Okay, let us start our BIMS Integrable System seminar. And today our speaker is Pavlo Gavrylenko from CISA about isomonodromic tau functions. So please, you can start.
Okay. Thank you very much for the invitation. So today I will tell actually several related stories about the isomonodromic deformations, and it will be based on the relatively old paper, actually on several papers of similar kind, and also on our recent paper. And also wanted to mention that I have a collaborator, Ideal, which is a very good student, and he is going to apply for a postdoc now. So if you see him, I would definitely recommend to accept him. So let me start with some kind of introduction to the topic. Okay, there is some plan of the talk. So the first part of the story is the following. It goes back actually to the beginning of 20th century, when people studied differential equations and systems of differential equations and their monodromies. And isomonodromic deformations. So the system we are interested in is the following. So the first equation is something like equation the Lark's pair, stating that y is an eigenfunction of A, but instead of the eigenvalue, we have a derivative, d in dz. So this is some linear system in the complex plane, and it is called a Fuchsian system. And there is also another equation, this one, which describes the evolution of this y in some parameter of the system. And it should remind the second equation in the Lark's pair that describes the evolution. So, as usual, we asked for compatibility of such equations, and instead of usual classical systems, this compatibility condition has three terms. So one is the commutator of A and B, another is time derivative of A. And in the classical system, it will describe the subjoint evolution of Lux. But in this isomonodromic setting, we also have a derivative of B of Z. So for example, because of this term, characteristic polynomial of A is not A invariant under this evolution anymore. And to be absolutely concrete, let us consider a very particular example of this system, and it will be the basic example throughout the talk. It is the example of a Penrose equation. So in this case, this matrix A has some generic matrix with coefficient 1 over z, and it also has higher order pose at 0 and infinity with Jordan block residues. So there is such a system, and it also contains this parameter t in one of the infinities, and it has double prime parameterizing matrix and other matrix elements. So this second matrix is of this simple form, and if you write compatibility conditions of them, then it gives the following nonlinear equation for W, which can be written as radial Sine-Gordon equation with this change of variables. So in principle, we could put some p on the diagonal and then solve this compatibility condition. But this will tell that p equals to logarithmic derivative of w, basically. So and why this system why the system is called isomonodromic? It is because the system in principle has a non-trivial monodrom is around 0. It also has a non-trivial Stokes data, which I'll explain on the next slide. But since this evolution in T is given by this equation, and the monodrom is act from the other side, computation of monodrom is commutes with the time evolution. So monodroms of the system are a kind of integrals of motion. So what kind of monodrom data do we have here? So if you look again at the system, we see this higher order singularities at 0 and infinity, and at infinity. And since they have only Jordan blocks on their non-diagonalizable matrices, then asymptotics of the solutions contains square roots. They behave like this. So there is dominant and subdominant solution at each infinity. And if a compute analytic continuation around 0 or around infinity for this pair of solutions, the one which should become subdominant in sense decaying exponential is defined uniquely, and the one which is which becomes big is defined up to this small solution. So modern matrices should have this form with 0 and 1 matrix element, and with trace written explicitly in the other matrix element. So you see that it's a matrix with a determinant 1 and trace 2 cosine of 2 pi a. So it's conjugate to diagonal matrix e to the plus 2 pi a e to the minus 2 pi a. And it's kind of cyclic normal form, which comes from this Stokes like computations. It was kind of local monodromy data around 0 and around infinity. And there is also some global data which tells us how to glue this 0 and infinity. Namely, there is one matrix which maps a basis of solutions at 0 to a basis of solutions at infinity. And it is given by this formula. It has one more parameter eta. And technically, this matrix conjugates m0 to m infinity. And so such matrix is defined up to one parameter, and this parameter precisely describes this relative position of solutions at 0 and to infinity. Are there any questions about this?
I'm sorry, the A parameter which is written here, is it in the system or is it arbitrary?
It is the initial data. A and data are initial data of the system.
Thank you.
Okay. They describe monodromies, and as we see from this slide, monodromies are preserved because monodromies act on the right and matrices act on the left. So, and now, namely, it looks like this system cannot be solved because it is some linear equation and some theorems about transcendentality of its solutions. In the sense that there is only one solution that can be written as a algebraic function. It is w equal to square root of t, which corresponds to trivial solution of this radial sine Gordon. But nevertheless, Gamayun, Iorgov, and Lisovyy found in 2012 and 2013 that solution of the system can be written explicitly using some non-trivial functions, Nekrasov partition functions of conformal blocks, in this case, degenerate conformal blocks. And the solution is described as follows. So first, this system has a Hamiltonian. And it is a general property of this isomorphic problems that Hamiltonian is a logarithmic derivative of some function related to some multi-valued function, which is called tau function. And another property is that such objects like W, which are called pennular transcendents, and objects that appear, for example, in the linear system. They can be expressed either as some logarithmic derivatives of tau or as ratios of some Backlund transformed tau functions. And Backlund transformation means that we consider these tau functions with different initial conditions. Well, if you have some, if system has some extra parameter, they can also be changed. So, so solution for the system is written as follows. This W of t is the ratio of two tau functions, and formulas for these tau functions are written in terms of a kind of Fourier transform of some function. So we have two initial data, eta and a, and this eta appears as a parameter of the Fourier transformation. It is in this exponential, and it's the only place where it appears. And another parameter a always appears as a plus n. So we have some denominator which consists of two bounce functions, and higher gamma function. We have some And this is called one loop part of partition function. We have some power of t, which is called a classical part. And we have some function of t, which is called instant on partition function, which I'll explain later. And also the difference between tau and tau1 is the range of summation. One is sum over integers, another is over half integers. There are these formulas, and the explicit formula for that instanton is this one. There's some over pairs of Young diagrams, y plus and y minus, and the sum is the following function of two product of the following functions of two Young diagrams. So it's some function of two diagrams and one complex number. It's given by explicit product over the boxes of one Young diagram or the boxes of another Young diagram, with the x shifted by some integer combinations of two parameters, epsilon1 and epsilon2. And so it is some general object. And if we are interested in this particular case, which is used in the tau function, we should substitute epsilon1 equals to 1, epsilon2 equals to -1. So generic epsilons correspond to some conformal block in CFT was, I missed squared here, sorry. It should be square in the numerator. So it's a central charge of conformal field theory, which appears for arbitrary epsilons. So I'm saying here conformal blocks and Nekrasov functions as synonyms, but they're related by the AGT correspondence. So it's not a real statement, but once it is known, we can just use this formulas that came from Nekrasov computation in the gate theory and use them in CFT. So they are just some explicit combinatorial formulas. And also the meaning of this epsilons, for example, if you put them with opposite signs, like epsilon minus epsilon, the meaning is that it is some overall scaling of parameters. So this that instanton and also the other part is homogeneous. And dimensions of this epsilons is an energy unit. It has dimension 4. It's also convenient, also for further considerations, to consider this product of all these terms, classical one loop and instanton. So it's better to consider this expression, which I call just z of a plus n t. Okay, so this is all about this first part. So the main message is that if you have some Isomonodromic system, you can write its solution in this explicit form. Explicit in the sense that it is some series with explicitly known coefficients. And there are several different proofs of this statement, more physical or more mathematical ones. So I think everyone can find the one which is more understandable. Are there any questions about this? Okay. So now let's go to the next part. So here I want to tell how to apply this science to quantum mechanical spectral problems. Namely, how to use it to find spectra of some potentials. So, and let me remind how it usually works in quantum mechanics. So usually we have some potential u of x, then we just try to solve the Schrödinger equation with this potential. It usually has two solutions. We choose that solution which decays on 1 infinity, for example, on minus infinity, so that it is some L2 function. And then open some book, for example, with connection formulas of hypergeometric function, or derive them ourselves, and find continuation of the solution to plus infinity. And you see that usually decaying solution is a combination of decaying and growing solutions. And to find the spectrum of this problem, we need to ask the coefficient in front of growing solution. It should be psi plus. Ask coefficient in front of growing solution to be 0. So it's a standard word. But if you try to use the monodromic deformations for this, logic will be literally reversed. So the things which we know at the beginning is this connection matrix between 0 and infinity, because we have already seen this 2 times 2 system with explicitly known monodromy data. So there was this matrix V, which mapped solutions at 0 to solutions at infinity and vice versa. Well, this is something known. Also, if we ask for this condition, in a sense, if we ask that a decaying solution maps to a decaying one, and we can look at the explicit form of this matrix, and I see that this condition means vanishing of one element, or two element. They vanish simultaneously. So it gives immediately this quantization condition. So the only question is what precise problem are we solving now? Because this matrix is written for the 2 times 2 system, and 2 times 2 system is not a second order equation. And we need to see what precise second order equation we get from that system. And so it's kind of the most naive idea. It is just to take the first element in this column that solves the system and say that it should be our wave function. We also noted that this way we get some non-trivial first derivative of it, and this can be fixed by division by square root of a12. And that if we finish writing this equation for y tilde, we notice that it contains something quite understandable. It is a trace of a of z squared half on this trace, and it is it corresponds classically to characteristic polynomial of a of z. Like we we can say that we are trying to compute a characteristic polynomial of dz minus a of z. But this also contains other terms. The most important terms are those that contain logarithmic derivative of a12. This is because a12 can have zeros. And literally, if you take explicit form of this matrix, which corresponds to penalty 3, and compute this potential, find that it has a second order pole at point W of t. So position of this pole is defined by the penalty transcendent. It's defined by W. And a modern at this pole is -1, which is clear from the definition of y tilde. Because originally we started from some solution that did not have any monodromies at W of t, because the system was just regular there. And now we have something that has monodromy -1. And the system contains some singularity. So if you ask about this quantum mechanical problem, then it turns out that it is not a normal Schrödinger equation. Not only the first term, but also something with this pole correction. And the parameters of this correction depend on everything. So it is something which we definitely don't like at the moment. And the problem of getting rid of this term is precisely this last point in the Isomonodromic approach. We need to find what to do with this extra correction. And the answer is kind of obvious. We want to send this pole to infinity or to 0. These points are actually equivalent. So now we choose to send it to infinity, which means that we need to take such value of t that W has a pole there. So if you heard about Pavlo classification, which originally gave all these equations, that he was classifying equations that don't have movable branch cuts or essential singularities, but they could have movable poles. And this pole at T star is precisely that movable pole. So we are interested in the point where W goes to infinity, which means that the second tau function, tau1, which is here in the denominator, this half integer sum, it should vanish. So on this point and its vicinity will be the object of our interest. For example, we can study this penal transcendent around this point. In some we just substitute this pole answer to the penal equation and see what happens. So this way we find that the first two terms are fixed by equation, and the first regular term is some arbitrary constant. And all higher terms are defined by T star and this constant. So, and if you compute the value of the Hamiltonian of this pole, it turns out that it is expressed in terms of this constant. So we can say that these two variables, position of pole of the spinor transcendent and the value of the Hamiltonian of this pole can serve as two initial conditions for such a solution. And it's enough because it's a second order equation. So, so there is this point and there is this solution. And also I forgot to say, but it's written that if go precisely to t equals to star, this potential will be cosine or cosh, and value of the energy is given by the value of this Hamiltonian. So if you compare this potential with the original Pavlo equation, we noted that one problem is a quantum autonomous system with cosh or cosine potential, and another is a classical non-autonomous system with the same potential. And it's not a coincidence, it is always like this. And also, one remark that here we are studying this cosh or cosine potential, but in principle, it can work, for example, for Launay equation with Weierstrass potential. And in that case, an autonomous parameter will be the modulus of torques. And it is written in that paper with Albert Kassi and Misha Emberstein, for example. Okay, so summary of this part is the following, that one way to solve quantum mechanical potential is to study solutions of the Isomonodromic system that have a pole precisely that have pole at some prescribed point. And if such solution, then they are described by position of this pole and the value of the Hamiltonian at it. Are there any questions about this part? Okay, so let's go further. So now I can tell a little bit different story, which is older than all this, but of course not older than the Pavlo equations. It is a story of it's a story about Nekrasov-Shatashvili quantization. So, namely, there is some other way to describe this quantum mechanical potentials, which is as follows. So we have this Nekrasov partition function that comes from the gauge theory. So I can maybe go back and show the formula again, although it is not used here, but explicitly. So the formula is this, and there is some instanton partition function, which is some explicit series dependent on two epsilons. And actually, for arbitrary epsilons, we should modify this formula. We should replace Barnes function with double gamma function with two parameters. So if you do this, and then take a limit epsilon 2 goes to 0, then this partition function exponentiates this way. Is e to minus 1 over epsilon 2 times some a function W, which can be called a twisted superpotential or a classical conformal block. Classical because central charge goes to infinity. And the Nekrasov-Saakashvili quantization can be formulated very easily. So there it's a function of two variables, A and T. And quantization condition says that A derivative of this function should equal to pi I n. And then if you find such A, actually such A's, there are many of them, then the energy is given by the time derivative of by the t derivative of this function. So that's all. It can be derived in many different ways. For example, if you know AGT, we can derive it also from conformal field theory. For example, we can consider this conformal blocks, this classical conformal blocks with degenerate fields, construct solutions of this quantum mechanical potentials and get these conditions. But let us suppose that we know this. So if we know this, and we know that S equals 1 quantization conditions, we can ask what is the precise relation between them. So in one case, we had some eta, which was monodramy data, and it should be quantized. In the other case, we have some function d of w, and it should also be quantized. And also, in one case, the energy is given by the logarithmic derivative of the tau function at this special point. In the other case, it is a derivative of this w. So if you look at this first condition, it is kind of natural to expect that these two are the same integer number. So it means that this point tau 1 equals to 0 it can be described in the following way. You should substitute for pi I eta equal to minus d of w, and the tau function will vanish. So at least this is consistent with both quantization conditions. And later I will tell how this can be derived from something that people already know. So we also have a kind of analogous statement for equality of these different equations for the energy. So we have some number of formulas of this kind. And the main thing about these formulas is that they relate conformal field theories with different central charges. So so duo corresponds to S equals 1 conformal block, and W corresponds to S equals infinity conformal block. And such kind of relations are called block relations. And they are known after the work of Nakajima and Ishioka. They derived these equations from some computation on the gate theory, but they also have alternative derivations from CFT due to work of Bernstein, Fig, and Litvinov, and also for different version of this equation due to work by Bernstein and Shechkin. But that equations are not used here. We'll use only Nakajima-Shioka relations. So these equations look like this. So it is so the first non-trivial equation contains the sum over all half-integer numbers, and the summand is a product of two Nekrasov partition functions over this conformal block with all normalizations. And what do we have here? We have two shifts of the argument of A. One shift is by epsilon1, another shift is by epsilon2. And we also have modification of the central charge or of these epsilons. The modification is on this one. Instead of epsilon1, epsilon2, we have epsilon1, epsilon2 minus epsilon1, and epsilon1 minus epsilon2, epsilon2. So such epsilons follow from geometry. So basically, these equations are called block relations because they appear when people try to compute partition function of the gauge theory on blown up C2 in two different ways. One way is to say that contribution of this blown up point can be can be computed explicitly as a contribution from a point and some operator inserted there. And another way is to use a localization formula on this blown up surface and localize to two different fixed points. And these different epsilons correspond to the action of the vector field used in this localization in the vicinity of two new stable points on the blow-up. But I don't want to go into the details. Also, because this formula can have different interpretations. For example, from the CFT point of view. So let's just think that this is something established. So we know such kind of formulas. Also, another example with integer summation is this one. So it tells that the left-hand side equals to this partial action on the original plane with non-modified epsilons. So there are such relations. Actually, there is an infinite number of them. They will show some formula that in principle describes at least some class of these relations. And now the question is how all this is related to the previous slide. So on the previous slide, we had some relation between c equals 1 and c equals infinity. And if you look at this formula, to see that if you put epsilon 2 equals to 0, then the first term becomes self-dual, because it's epsilon 1 minus epsilon 1. And the second one becomes c equals infinity or Nekrasov Shvili. But this can be done a little bit carefully because this epsilon 2 appears in several different places. So if you look at the term that becomes Nekrasov Shvili, then we see that there is some singularity in the exponential 1 over epsilon 2, and we need to expand all the other terms around this singularity. So we see that there are two terms of this Taylor expansion that give some finite contribution of this pole term cancels, and we have minus n dA of W, which is precisely what we need, and the epsilon 1 of W. which is the overall factor. So if it is some vanishing condition, then this factor doesn't matter. But if it is not, then it says that if you normalize the star function by this factor described by a classical conformal block, then it is normalized by 1 at this point where the other tau function vanishes. So in some sense, this conformal block gives some explicit description of a zero of the tau function. Are there any questions about this? Okay, so let's go further. So we can also use this block relations to describe this expansion of the tau function around its zero. So here we introduce a little bit different variables, namely we introduce some variable lambda of dimension 1, tau is lambda to the fourth. And we also introduce the so-called block factor. It's the ratio of two partition functions, and so numerator has this form of block relation, but with modified lambda. It is written in this symmetric way. In a sense, one term contains shifts by epsilon1, another term contains shifts by epsilon2, and it has some gauge-Taylor interpretation. So this ratio is called block factor. And if we take Nekrasov's limit of this, we see that tau function is closely related to this block factor, and this tau function is just e to the US over epsilon times b. So it's almost the same. And this tau function vanishes when s equals to 0. Because when we substitute s equals to 0, this becomes precisely this vanishing block relation. So it is some way to give explicit description to this tau function parameterized by a position of its 0. And this block factor also has some explicit formula that probably follows from the gauge theory, but I think it was originally obtained from CFT in the paper I mentioned. So this block factor can be written as some differential operator depending on S that acts on Z. And if you take, so it is some polynomial on lambda in the D&D lambda. And again, if you take the Nekrasov's limit of this operator, we see that our factor is given by some series in S with coefficients that are functions of U and lambda. And the U again is the Hamiltonian, the value of the Hamiltonian. So summary of this part is the following. So this C equals 1 and C equals infinity quantization conditions are equivalent because of this C equals infinity limit of the block equations. These block equations themselves, even without relation to quantum mechanics describe positions of zeros of isomonodromic tau functions in some more or less explicit form. And if we try to expand this tau function around the zeros, then the only parameters of this expansion will be position of zero and the value of the Hamiltonian. So there are local parameters around that point. And so it should be compared with this original Kyiv formula where the tau function was parameterized by monodromic data. Those expansion around zero can be described in a different way. It can be described in terms of U and lambda. So we actually had the statement in the previous part, but we could also see it from this different point of view. So, are there any questions about this? Okay, now let's go to the last part. So now we would like to study a kind of quasi-classical limit in all possible sense of this partition of this Nekrasov partition function, and this description looks like this. So there are two parameters of expansion: minus epsilon 1, epsilon 2, and epsilon 1 plus epsilon 2. And this tau function is this infinite series over integer g's and integer non-negative integer g's and non-negative integer n's with some extra term for n equals 1/2, g equals 0, k equals 1/2. So this double expansion. So there is some interpretation of this G as a genus of some curve, and well, maybe. Well, in principle, yes, we can say this. If it is yes, if we derive such formula from some topological strings, then this minus epsilon 1, epsilon 2 will be the string. And this genus will be a genus of the worldsheet. But in principle, we can say that it is just some expansion of the same kind as we have in the matrix models. So it is some typical form of expansion, and if you look at some special cases, we can put, for example, epsilon 1 plus epsilon 2 equals to 0, and then we will have only this 0-point contributions, FG0. It will be a self-dual case. Or we can put epsilon 2 equals to 0. It will mean that the only surviving terms will correspond to G equals to 0, and all possible cases. It will be a Nekrasov-Schwieri limit. So there are kind of two x's that correspond to the expressions we have already seen. And the zeroth term in this expansion is described by the Gavrylenko geometry. It was the first object that appeared in the Gauge-Taylor studies, and then Nekrasov added this epsilons to be able to perform instantaneous calculations. So this first term is described by the Gavrylenko equations. So there is this curve with a differential. It's some elliptic curve with branch points u. Sorry, it should be lambda force. U and lambda plus minus lambda squared. And so there is this zero contribution, and the point is that all these other contributions can be written explicitly. So not as a series in lambda, but just as some modular and quasi-modular functions of a period of the Zebra-Witten curve. These functions have this form. This function, the basis of functions is this. And so the main thing is that one of these functions is E2. It is a logarithmic. It is, for example, a logarithmic derivative of the Dedekind eta function, and it also appears in any logarithmic derivative of any modular function with a non-trivial weight. So this E2 is a quasi-modular form. And these thetas and Einstein series are modular probably with respect to some smaller subgroups. Also, in principle, we can make this E2 modular, but the price we should pay is that it now becomes non-holomorphic. But non-holomorphic in some simple way. So these are these functions that appear in this description. And if you want to see the explicit terms of this genus expansion, they are known. So if zero is something complicated, it contains, for example, tau explicitly this quasi-modular function x, modular function u, something of non-zero modular weight. And then if you go to higher orders, then this function start to disappear. So this 0, 1, and 1, 0 contains some logarithms, but if you go to higher orders, they are just some polynomials of x and u multiplied by some power of u squared minus 1. So there is such kind of expansion. It is known, it can be computed, it can be obtained from comparison with this instant. An expansion, in a sense, we can take this ansatz from the last line and substitute Zebra-Witten period for the degenerate curve and find first such FGNs. And now I would like to use this expansion in these tau functions. So actually there are two tau functions. One is the one which I studied originally. It is the tau function that has 0 at s equals to 0 and it is normalized to 1. It is obtained by substitution of rho and alpha in terms of this full NS partition function. And the statement about this function, which I wrote several times, is that it depends on everything only in terms of u, which is this u ns, lambda, epsilon, and s. So this statement means that we should have the following equality for its derivatives in E2 and in some other variable, for example, A. But actually, it's easier to study an example of the tau function, which for some reason is also nice. The tau example is when we keep only the leading term, and this genus 0 point terms in alpha and rho. Since we substitute everything in terms of Zebra-Witten. So, and now we would like to compute the sum. So, there is some remark about computation of the sum. So it is some theta function like formula. And we know that there are two elliptic functions, or at least two. There are theta functions that are given by some Fourier series, and there are sigma functions, which differ from theta functions by some quadratic exponentials. And the important difference between sigma and theta is that sigma is a holomorphic function. It does not contain E2. It contains E4, E6, and the polynomials of them. And theta function contains E2. So if we now use this knowledge, we can compute this sum. So actually, we did this computation for the full partition function, for the full tau function, and I want to show it for this two example. So the idea is the following: if you want to take this theta-like series, we need to expand the sum and as a series in n up to the second order, because it is the first term which is regular in epsilon, and then say that everything else is a correction. This correction can be written as a pairing of some differential operator, which consists of sigma function and this e2 over 24 p squared, and this stable part, which contains terms of epsilon, epsilon squared, and so on. And if we now know that this does not depend on E2, we can simply write a differential equation that 0 equals to dE2 of this tau Weber-Witten. And then when we differentiate this, we have two contributions. One is from derivative of the sigma function, another is from a derivative of this partition function or conformal block. And we know that it is 0, which means that this conformal block, a stable part of it satisfies this differential equation, which is called holomorphic anomaly equation. And originally it was obtained from some topological strings. So it was something absolutely non-trivial. So we had to pass from the gauge theory or from CFT to topological strings, compute something there. But here it is simply a consequence of this a simple dependence where everything is encoded in the variable u. So in the sense, we can get this holomorphic anomaly equation for free from this Isomonodromic CFT correspondence. Okay, so thanks for your attention.
Okay, thank you for your talk. Questions? Chat questions is just spam. So let me ask. So that zeros of isomonodromic tau functions corresponds to quantization conditions in the some spectral problem.
Yes.
The last part was about some expansion near zeros.
Yes. So we can also say about this expansion that there's some expansion around autonomous system, because you see that this answer contains sigma function, and a sigma function is a solution of autonomous system. This epsilon is a parameter of that parameterizes kind of non-autonomousness of the system.
Yeah, and could you please clarify the statement? What we can know from this expansion near zero? So we have an equation on
this partition function that is used to write the formula for the tau function. So basically, this E2 dependence comes from two places. One is the relation between theta and sigma, and another is this partition function itself. And we know that the final formula does not contain E2. So it should somehow cancel. And this cancellation condition gives precisely the holomorphic anomaly.
Okay, thank you. Any other questions? Okay, if not, let's thank our speaker again.
Thanks for your attention.
Yeah, we will also need your slides.
Okay.